Welcome to the next session, my dear friends. So in the previous session we were discussing about the efficiency, how to calculate the efficiency. In efficiency term we know what is V naught, but we don't know what is Vs. So let us see how to determine Vs. Vs is the settling velocity. Generally Vs is determined using the terminal velocity concept. Terminal velocity concept which was defined by the Stokes. Okay, so the same Stokes law we have already learnt in our soil mechanics. Okay, the same logic we will apply here also. So as per Stokes law, so Vs is settling velocity we determine using terminal velocity concept. Terminal velocity concept defined by Stokes. So the same Stokes law here also we will recall. So according to the Stokes law, what are the assumptions we have made in the Stokes law? According to Stokes law, when a particle is falling, when a spherically shaped particle, if it is falling from infinite height, when it is falling from infinite height, then after traveling some distance, okay, so it will attain a constant velocity. Thereafter it will move with that constant velocity. That velocity is called terminal velocity, which we have discussed it elaboratedly in soil mechanics. That is why I don't want to recall all that thing here. So here the settling velocity given by the Stokes. What is the settling velocity given by the Stokes? So settling velocity Vs is equal to G into rho s minus rho w into d square by 18 mu. So what is G here? So G is acceleration due to gravity. G is acceleration due to gravity, and D is the rho s is the density of particle or impurity, and rho w is density of water. D is diameter of the sediment or particle, diameter of sediment or the particle or impurity, whatever it may be, or the particle. Mu is dynamic viscosity. So the same formula can be written like this also. So if this G goes inside, so then it is gamma s minus gamma w into d square by 18 mu. Or else we can write it in other way also. So this is the dynamic viscosity of a fluid. See, this is dynamic viscosity of water. Here this is the viscosity of water. So if I take rho w as common, then this formula will become, so if I take from this formula G into rho w, if I take it as common, it will become rho s rho w minus 1 d square by 18 mu. Okay, so this can be written as, so this is specific gravity and this rho w comes down, it will become mu by rho w. Okay, g into, this is specific gravity s minus 1 d square, g into s minus 1 18 mu by rho w. So this rho w will come here as a denominator, mu by rho w. So this is called kinematic viscosity. This is called nu, kinematic viscosity, which is equal to, the same formula can be written as g into s minus 1 d square by 18 nu. So this is also settling velocity formula. Okay, so g into s minus 1 d square by 18 nu. So where s is the specific gravity of the sediment, specific gravity of sediment, specific gravity of sediment, and nu is the kinematic viscosity. Nu is kinematic viscosity. Nu is kinematic viscosity. Okay, so these are the basic formula to determine the settling velocity as per the Stokes law. Settling velocity as per the Stokes law. So let us write the formula again clearly. So there are some other formulas also. Generally, during the derivation of the terminal velocity formula, Stokes has assumed that the flow is laminar and the Reynolds number is less than 1. Okay, so during the derivation of this terminal velocity, terminal velocity or settling velocity Vs, which is equal to g into rho s minus rho w d square by 18 mu, or g into s minus 1 d square by 18 nu. Okay, so this is valid when the diameter of the sediment is less than or equal to 0.1 mm and when the Reynolds number is less than 1. So when the diameter of the sediment is less than or equal to 0.1 mm and the Reynolds number is less than 1. So for that purpose, for that condition, these are the formulas. If there is a change in the viscosity, because here the equation, it is dependent on viscosity, either it may be dynamic viscosity or it may be kinematic viscosity. So viscosity is susceptible to temperature. Okay, so viscosity is temperature dependent. So that is why, so the Stokes, whatever the settling velocity, okay, settling velocity varies with the temperature. varies with temperature. That is why along with Stokes, Hazen also given some equations for settling velocity. Considering the temperature, Hazen has given some kind of settling velocity equation. Okay, so Hazen has proposed some equation of settling velocity. For settling velocity. So as per Hazen, what is the formula of settling velocity? The Hazen's equation, Vs is equal to 418 s minus 1 418 into s minus 1 d square into 3t plus 70 by 100. 3t plus 70 by 100. This is an empirical formula. And this formula we need to use when d is less than or equal to 0.1 mm. D is less than or equal to 0.1 mm. And same settling velocity was given another formula. Hazen has given another formula, 418 s minus 1 into d into 3t plus 70 by 100 when d is less than 1 but greater than 0.1 mm. So if it is in between 0.1 mm, less than 1 mm. Here these are empirical formulas, so all the units are very, very important. We need to take Vs in mm per second, so you will get Vs. So when we substitute d in mm and t in degrees centigrade, so we need to substitute t in degrees centigrade and d in mm, then we will get Vs in mm per second. So d we need to substitute in mm and t we substitute in degrees centigrade. We will get the Vs in terms of mm per second. So when the d size of the sediment, diameter of the sediment is more than 1 mm, then Vs is equal to 1.8 square root of g into d into s minus 1. So 1.8 square root of g into d into s minus 1 when d is greater than 1 mm. So this is the settling velocity formula, because here when the diameter is more than 1 mm, it may cause some kind of turbulence also. Okay, so that is why we have taken this formula, or Reynolds number is greater than 1000. So when the Reynolds number is greater than 1000 means we have entered into transition flow, so also turbulence also present. Okay, so that is why, so these are the settling velocity formulas. These are the different kinds of settling velocity formulas we are having. So we are having the most important formula, which is very, very frequently asked in the GATE examination, that is Stokes terminal velocity formula only. So that is very, very important. And little more important is Hazen's formulas, that is Vs formula. But when the diameter is greater than 1 mm, that thing may not be possible in the sedimentation tank, that condition may not arrive. So that is why generally that equation is not that important. Vs is equal to 1.8 into square root of Zd into s minus 1. That equation is not that important, but the settling velocity formulas 1, 2 and 3, these are very, very important for the GATE examination. Okay, so now analysis of particles. So when the particle is having, so now we have calculated, we now understood how to calculate Vs, we know how to calculate V naught. So that means we can calculate the efficiency now. We can calculate the efficiency now. So if the particles which are having lesser efficiency, for example, if the efficiency it is coming 100% or more than 100%, then it is okay. That means all the particles are settling in the settling tank. If the efficiency is coming less than 100 means all the particles are not settling in the settling tank. Some particles are settling, some particles are escaping. How to know which particles are settling, which particles are escaping? How can we find that? How many particles, for example, if 30% is the efficiency, then what is the 30% indicates? How can we understand that? So let us see that. Analysis of particles having efficiency less than 100%. Analysis of particles having efficiency less than 100%. Having efficiency less than 100%. So if you take a tank, if you take a settling tank, so three different particles, this is a sludge zone, so three different sized particles A, B and C, all are started traveling. A, B, C, all the three particles started from here, A, B and C. The particle A is settled somewhere here. The particle A settled here. This is the movement of the particle A. And the particle B has traveled like this. This is the path of particle B. So particle B, this is particle B, has met the bottom of the settling tank here. Another particle C has traveled like this. So this is path of particle C. So depending upon the settling velocity and the flow velocity, for all the particles, see, for all the particles, this is one particle, this is another particle, this is another particle, this is another particle. For all the particles, Vf is same. All the particles, flow velocity on the particle is same, because flow velocity is the property of what? Flow velocity is the property of the settling tank, sedimentation tank, not of the particle. But Vs, here it is larger particle will be having larger Vs. This particle is little smaller, so it will be having little smaller Vs. This particle is much more smaller, it is having Vs 2, 3. So this is very small, Vs 4. See here, in comparison with Vf, Vs is very large. So the influence of Vs on the resultant. So this is called resultant motion. This is called the resultant path of the particle. So if Vs is larger, then the particle resultant will travel towards the major component only. So that is why if you see here, it will travel like this. If you see here, so it is also larger, but not that much of this. So that is why slightly it moves towards the flow velocity. Here it is again larger, but comparatively very small difference is there between Vf and Vs. So that what happens, the flow velocity tendency now, the influence of flow velocity will be little more. Here the influence of flow velocity on the resultant is very minimum, because settling velocity is very high. The influence of flow velocity on the resultant is very minimum, because this value is very high. Here the influence of the flow velocity little bit increased, because of which the resultant little bit moved upward. Here the flow velocity influence much more increased, so little bit the resultant has moved up. Here the flow velocity is dominant, so that is why what happens, the resultant will be towards the flow velocity. So this resultant direction is nothing but the particle movement in the sedimentation tank. Particle movement in the sedimentation tank. So this is now again V naught. Again if you see V naught again everywhere it is same. For a sedimentation tank, V naught is same. So for example, so this is the V naught value. So this is the V naught value. Everywhere you see V naught is same. Everywhere you see this is V naught. So if this Vs is more than V naught, then it will settle faster. If Vs is more or less equal to V naught, then it settles at just at the exit point. When V naught is more than Vs, then this particle may not completely settle down. Some amount of particle will settle, some amount of particle will escape. Here this also V naught is much more than the Vs, so majority of the particles will escape. Very few amount of particles will settle for this condition. So these are the comparisons between V naught and Vs. Okay, so we need to understand how to differentiate V naught and Vs. What is Vs and what is V naught? That thing we need to understand. Now here, so when the efficiency is less than 100, that means this one C, particle A, here Vs is greater than V naught. For particle A, Vs is greater than V naught. That means Vs is greater than V naught. That means the particle will settle in advance. So in the second case, B, if you see B, Vs is exactly equal to V naught. For this, Vs is equal to V naught. For this, Vs is greater than V naught. For this, Vs is less than V naught. So if Vs is greater than V naught, though the efficiency is 100%, Vs is equal to V naught, though the efficiency is 100%, Vs less than V naught, for this the efficiency is not 100%, it is less than 100%, for which we are doing the analysis. Now here this particle C, let us only see the particle. Let us see only the particle C. Okay, so let us redraw this only looking at the particle C. This sludge zone. So this is particle C. So it is coming somewhere here. So this is the height of the settling tank. This is the height of the settling tank. Okay, we don't consider the sludge zone in settling tank. So this is the height of the settling tank. Now, so if this is the height, there is a depression here. So the particle is coming down to a height h. Okay, so during the travel from here to here, the particle is moving vertically downward to a height of h. Now what I will do, I will draw a parallel line to this. What I will do, now I will keep this particle, I will keep this C somewhere here. So let us take, this is C dash. I have taken this particle C somewhere here at a height of small h from the bottom. So this is how much? This is small h from the bottom. So if this is the line of resultant, the same will be the line of resultant here also. The same will be the line of resultant here also. They both are parallel. That means if you keep the particle at C dash is exactly touching, because is exactly touching at the bottom of the settling tank, because when it is traveling a length of L, it is having a depression of H. So that is why when I see the particles up to the height H from the bottom, they will be having a depression of H such that they will meet the bottom of the settling tank. That is what is our assumption. That means if this is the topmost particle which is just hitting the bottom of the settling tank, then all the other particles present here, all the other particles of C dimension, size of C, all the other particles of size C present in this zone will 100% settle. So that means when the efficiency is less than 100, then how many particles will settle? So these particles, that means this efficiency can also be determined as Vs by V0 into 100, or the same efficiency can also be written as small h by capital H into 100. Small h by capital H into 100. Okay, so earlier in the previous figure I have shown three particles: particle A, particle B, particle C. So particle B is exactly meeting the bottom of the settling zone. Particle B is exactly meeting the bottom of the settling zone. Earlier if you see the figure, so this is particle B, exactly it is meeting the bottom of the settling zone. This is particle A, this is particle C. So the diameter of this particle B, so the diameter, dia of particle B is taken as dia 100%. Dia of particle which settles 100%. This is the minimum diameter, okay, dia of the particle B, because particle B is the boundary. Particle B is the boundary. C is above this boundary, A is below this boundary. So diameter of the particle B is taken as the minimum diameter, minimum dia to have 100% settlement. To have 100% settlement. This is the minimum diameter. So this is called d 100%. So when the diameter of any particle, so dia of any particle greater than d100 will completely removed. So when the dia of any particle, if it is less than d100%, then 100% removal is not possible. 100% removal is not possible. That is why here we need to either compare it with Vs and V0, or we compare it with D100 and D. Any comparison we can do. Either this comparison, from this comparison also we can say whether the efficiency is less than 100 or not, or this comparison also we can do, or this comparison also we can do. There are different formulas for finding the efficiency of the sedimentation tank. There are different formulas to find the efficiency of the sedimentation tank. So this is the efficiency of a sedimentation tank when the N, eta, the efficiency is less than 100%. Okay. So sometimes they will ask the overall efficiency of a sedimentation tank. For example, they will give some percentage. see d1 diaparticle, okay, it is x1 percentage. D1 diaparticle is x1 percentage out of all the particles with efficiency of eta 1, and x2 particles, D2 diaparticles with x2 percentage having an efficiency of n2 percentage. Similarly, D3 diaparticles x3 percentage with eta 3 percentage. What is the overall efficiency of sedimentation tank? Overall efficiency of sedimentation tank, eta is equal to x1 n1 plus x2 eta 2, x1 eta 1 plus x2 eta 2, x3 eta 3 by x1 plus x2 plus x3. So this x1 plus x2 plus x3 should be equal to 100. This x1 plus x2 plus x3 should be equal to 100. Likewise, we will find the overall efficiency of the sedimentation tank. So this is all about the analysis of the sedimentation tank. Let us go to the design parameters. Design parameters of sedimentation tank. Design parameters of sedimentation tank. Design parameters of sedimentation tank. So what are the different values we have seen for sedimentation tank, like overflow velocity, detention time, flow velocity, length to depth ratio? All these things are the design parameters. Okay, so the overflow velocity V0, overflow velocity for a sedimentation, for a plain sedimentation tank, for a plain sedimentation, this is plain sedimentation. These are the design parameters of plain sedimentation, not for sedimentation aided with coagulation. So the overflow velocity is 500 to 750, 500 to 750 liter per hour per meter square. Liter per hour per meter square, or 12 to 18 meter cube per day, or 12 to 18 meter cube per day per meter square. Meter cube per day per meter square, that is overflow velocity. Next is detention time, dt. Detention time. So detention time should be equal to 4 to 8 hours. 4 to 8 hours. So how to find this detention time? So detention time dt is equal to, detention time is nothing but volume of the tank by discharge of the tank. So volume of tank by discharge of the tank. Okay, volume by discharge, V by Q. It is equal to V by Q. V by Q. So that is detention time. Next is flow velocity. Flow velocity. Flow velocity. Flow velocity is equal to 0.9 to 0.2 to 0.9 meter per second. 0.2 to 0.9 meter per second. Generally, we prefer Vf as 0.3. Generally, Vf is equal to 0.3 meter per second. Generally, Vf is taken as 0.3 meters per second. And length to width ratio L is equal to 4b. So our L by B is equal to 4 generally. So L depth is generally taken as depth. Generally we keep it as 3.0 meter. So length and width ratio will be equal to 4. And for sludge zone, we keep 0.8 to 1.2 meter extra. So we keep for sludge zone, apart from the depth 3 meters, we keep 0.8 to 1.2 meter extra for sludge deposition. Okay. So these are the design parameters. These are the design parameters of sedimentation tank, that is plain sedimentation tank. There are some other terms we need to understand in plain sedimentation tank. That is, first one is flow through period. Flow through period. What is flow through period? Actually, we thought that when a particle entered into a sedimentation tank, so when it is going out of a sedimentation tank, it will travel along the length L. But in reality, the particle may not travel in the proposed direction, okay, with the proposed velocity, because the particle, it is a continuous type of sedimentation tank. What happens in actual, the particle is pushed by the incoming flow of water. So the particle is designed to travel with the flow velocity, but what happens, the person who is coming from the back, the water which is coming from the back will push this water forward. We don't consider that, because of which the actual travel time, okay, the actual travel time of a particle from inlet to the outlet of a sedimentation tank may be less than the detention time. That is called flow through period. Okay, that is called flow through period. So flow through period, it is the actual time taken by a particle to travel from inlet to the outlet. To travel from inlet to the outlet of tank. It is always less than detention time. It is always less than detention time. dt, because the flow is accelerated. The flow is accelerated by many factors, such as thrust of incoming water, wind force or wind drag, change in viscosity, etc. Change in viscosity, etc. So because of which the particle may not travel with the detention time. It takes lesser time than the detention time. That is called flow through period. Okay, flow through period. So this is also called as short circuiting. See, this short circuiting, due to the short circuiting of top layers, see, generally whatever this happens predominantly in the top layers. If you go to the bottom layers, the incoming fluid thrust or else wind drag, all these things may not be predominant in the bottom layers, but it is predominant in the top layers, where the dt will be very less than the designed detention time. Okay, than the designed detention time. So displacement, next is displacement efficiency. What is displacement efficiency? It is related to flow through period only. The displacement efficiency is equal to flow through period by detention time. Flow through period by detention time. That is nothing but displacement efficiency. For a normal sedimentation tank, this displacement efficiency is 30%. In general, displacement efficiency is 30%. In general, displacement efficiency is 30%. Okay. So, what are the factors that affect the efficiency of sedimentation tank? And also, this is all about the rectangular sedimentation tank. What is the analysis part of circular sedimentation tank, that we will discuss in the next class. In the next class, we are going to discuss the factors affecting the efficiency of this rectangular sedimentation tank and analysis of the circular sedimentation tank, that we will discuss in the next class. Thank you so much.